Hello, everyone. Welcome to our presentation for WACV 2026. Today, I am excited to present our paper titled PatchEAD, Unifying Industrial Visual Prompting Frameworks for Patch-Exclusive Anomaly Detection. This work is a collaboration between Inventec Corporation and the University at Albany, SUNY. The authors include Po-Han Huang, Zhenglin Li, Po-Hsuan Huang, Ming-Ching Chang, and Wei-Chao Chen. In this session, we will introduce a novel, vision-only framework designed to streamline industrial anomaly detection by removing the dependency on complex textual prompts. Let's begin with the background. Industrial anomaly detection is critical for modern manufacturing. Traditionally, as seen on the left side of the slide, detection methods were training-heavy. They required collecting extensive category-specific data, often needing thousands of defect-free images, to train a specific model for a specific domain, like a circuit board or a screw. However, we are currently witnessing a paradigm shift. We are moving toward Foundation Model AD. This new approach leverages large models pre-trained on vast, diverse datasets, such as CLIP or DynoV2. These models offer generalization, enabling zero-shot or few-shot inference. This means we can detect defects in new products without retraining the model, simply by providing a few reference images or prompts. While foundation models are powerful, current implementations face two significant limitations. Limitation 1 is the reliance on textual prompts. As shown on the left, methods like Anomaly Clip require engineers to craft specific text descriptions, such as find defects like scratches or dents. This is ambiguous and difficult to tune for subtle industrial defects that are hard to describe in words. Limitation 2 is the inconsistency of visual pipelines. Different backbones often require different processing setups. This leads to our key question: can we build a unified, vision-only framework that works across diverse foundation models without any training? We believe the answer lies in simplifying the process to a direct patch-to-patch comparison. Here, we compare our approach against existing state-of-the-art methods. The top section illustrates multimodality methods. These typically use a text encoder to create embeddings for prompts like a bottle with damage. This introduces complexity. You need a text encoder, an image encoder, and you must calculate cross-modal similarity. It relies heavily on the quality of the handcrafted text prompt. In contrast, look at the bottom section, our PatchEAD approach. We discard the text branch entirely. We ask, is patch information enough? Our method relies solely on the vision encoder. We extract patch embeddings from the image and perform a direct patch-wise similarity comparison against a reference. This removes the ambiguity of language and focuses purely on visual deviations, making the pipeline cleaner and more precise. This slide details the architecture of PatchEAD. We designed it to handle two distinct settings, few-shot and batch zero-shot. In the few-shot setting, top, we have a query image, the screw, and a few normal prompt images. First, we apply an optional alignment step to correct rotation. Both query and prompt images pass through a shared frozen backbone, like DynoV2 or CLIP. We extract patch embeddings. Instead of using a global image vector, we flatten these patch embeddings. We then calculate the cosine similarity between the query patches and the prompt patches. The maximum distance indicates an anomaly. This generates a patch anomaly score map. In the batch zero-shot setting, bottom, we don't have a predefined golden set. Instead, we take a batch of unlabeled images. We treat each image as a query and use the rest of the batch as the reference set, assuming the majority are normal. This unified flow allows us to plug in any backbone without architectural changes. To make this vision-only approach robust, we introduce visual prompting techniques. The first is alignment. In industrial scenarios, parts on a conveyor belt are often rotated or shifted. If we compare patches directly, a slight rotation creates a false positive at the edges of the object. We utilize a standard ORB feature detection and matching pipeline. We estimate the affine transform between the reference and the query image. We then calculate the angle and shifts to counter-rotate the image. This ensures that we can find the similar patch in the query image and reference image. We are looking at the exact same physical part of the object. The second visual prompting technique is attention-guided masking. Background noise is a major source of false alarms. To solve this, we extract the final attention layer from the backbone itself. As you can see in the heat map examples, Models like Dino V2 naturally focus on the object foreground. We normalize these attention scores and apply a threshold. This generates a binary mask that suppresses the background. By applying this mask to our anomaly score map, we eliminate interference from the conveyor belt or table surface, ensuring the model only hunts for defects on the object itself. We conducted extensive experiments to validate PatchEAD. We used 7 major datasets, including the industry standards MVTECAD and VIS-A, as well as MPDD, BTAD, and others. We tested both batch zero-shot and few-shot scenarios. Also, we evaluated a wide range of models, including CLIP, DynOV2, DynOV3, and PE_spatial to prove our framework is model agnostic. Our goal was to compare against top-tier methods like WinClip, Anomaly GPT, and MUESC. Let's look at the few-shot results on MVTech and VIS-A. The table compares our method against training-free methods and training-based methods. Please look at the rows for PatchEAD Plus at the bottom of the 1-shot, 2-shot, and 4-shot sections. In the 4-shot setting, we achieve an image-level AUC of 97.0% on MVTech and 91.9% on VIS-A. This significantly outperforms WinClip and is highly competitive with, and sometimes beats methods that require extensive training, like PatchCore. This confirms that 4 normal images and our patch-based framework are sufficient for high accuracy detection. Next, we examine the batch zero-shot results, where no prior reference set is provided. Here, PatchEAD Plus achieves an average AUC of 91.5% across all datasets, highlighted in bold red. Compare this to WinClip at 81.6% or MUESC at 89.5%. Our method demonstrates superior generalization. By simply using the statistical properties of the batch itself as a reference, PatchEAD effectively identifies outliers without any human supervision or handcrafted text. We also analyzed the robustness of our framework. Top table shows the impact of different backbones. While we get the best results with Dino V3 and PE_spatial, the performance is consistently high across all modern backbones, proving our unified claim. Bottom table looks at image resolution. Increasing input size from 224 to 672 improves the AUC because it increases the effective resolution of the patches, allowing the model to catch smaller defects. However, we found that 448 by 448 offers the best trade-off between accuracy and computational efficiency. Ideally, we want to see the anomaly clearly localized. In this figure, the second row shows the ground truth. The third row is the standard PatchEAD. The fourth row is PatchEAD Plus. If you look at the KSDD or DTD-SYN columns, you will notice that PatchEAD Plus produces much sharper heat maps, shown in red, that align almost perfectly with the ground truth. The alignment module successfully removes false positives at the edges that appear in the standard version. Finally, we conducted an ablation study to validate our visual prompting design. As detailed in Table 5, our experiments confirm that both the alignment and masking modules are effective. Specifically, alignment enhances the image-level detection accuracy, while masking improves pixel-level localization. By integrating both modules, PatchEAD Plus achieves its highest performance, demonstrating that these visual prompts are essential for robust anomaly detection in complex industrial environments. To conclude, we have proposed PatchEAD, a unified, training-free, and vision-only framework for industrial anomaly detection. We successfully reduced the dependency on text prompts, solving the ambiguity problem. We unified the pipeline, making it compatible with diverse foundation models like Dino and CLIP. We achieved state-of-the-art performance in both few-shot and zero-shot settings using our enhanced visual prompting techniques. For future work, we plan to extend this patch-based approach to 3D point clouds and video anomaly detection. Thank you very much for your attention. You can scan the QR code to read our full paper and access the code.